Hey everyone, welcome to Everything is Relative with me, Mr. K. Today we'll be looking at CAIE or Cambridge A-Level Physics 9702, and we'll be doing a crash course on the topic of astronomy and cosmology. Now this is a fairly recent addition to the syllabus, but it still covers a lot of content. And to be fair, astronomy and cosmology is a popular research option for people who are intending to study physics at a university. And so it is quite important. That's why it's part of the syllabus. Now, basically, in this topic, we are only being introduced to things that mostly relate to stars, but could also relate to other celestial objects. And specifically, we want to know how bright stars are, what their composition is, what size they are, how far away they are, etc. And it's surprising, really, that although these numbers that we use and these magnitudes that we get are surprisingly large and cosmologically large, we still have fairly basic ways of determining these magnitudes, as we'll see as we do this crash course. So the first thing we need to talk about is a standard candle. And so I have a very accurate diagram of a star. And this could be any star. It could be the sun, could be Rigel, could be Betelgeuse, could name a star, it could be any star. And a standard candle is simply an idea of how bright a star is. So let's write this down. Now, a standard candle is simply anything in the observable universe that we can look at, we can observe, and tell the brightness of. If I know the brightness of something, I can compare the brightness of anything else I see with that something. You know that if I place two candles in a room, one closer to you and one further away, although they have the same absolute brightness, although the actual brightness being emitted from the candle is the same, what we observe will be different. The candle further away would look dimmer, and the one closer to you would look brighter. And so we use standard candles as things in the universe that we know the brightness of to compare other things to. So let's first talk about something called luminosity. Let's take a star, for example. We know stars are bright balls of gas, and we can say that this quantity, luminosity, which we have not learned before, we'll give it the symbol L, is the energy per unit time that is emitted by a star, or simply the power radiated by a star. Stars are very powerful objects, give off a lot of energy. And when we say energy, let's keep this to light energy, or energy that's in the form of electromagnetic or EM radiation. So that's the energy that we're talking about that's being emitted every second or per unit time. And so there's a idea behind, well, if I look at a star, irrespective of where it is, I'm going to extend these rays of light outward very poorly. And if I were a distance, let's call it d1 to the star, and then a slightly further distance out d2, if I had two different observers looking at the star, d1 is a distance that's less than d2, then what I observe is at distance d1, if I draw the arc of a circle that has radius d1, and I draw the arc of another circle that has radius d2, you'll probably see this in your textbooks. What I get is that the light, like a candle light would, like all light sources do, all good light sources spread out equally in all directions, very similar to a sound wave does. Lasers are an exception to the rule. Lasers are directional light. They are meant to be coherent directional sources of light. But stars are not. They shine out equally in all directions. And so the light that's being emitted from the sun over a distance d1 then occupies an area a1, a surface area. The light covers a surface with area a1, but after traveling a distance d2, which is a greater distance, the light covers a much larger area. And so this area we'll call A2, and A2 is clearly larger than A1. And so what we can see is that this area A1 over A2, if this is a circle and this is a portion of a circle, then the ratio of the areas is equal to the ratio of the square of the distances d1 to d2. So A1 over A2 is d1 squared over d2 squared. And so what we can see is that as you get further out, the light spreads over a greater distance. Now, what this means is we know that a person who is observing from a distance d2 will observe a dimmer light. Okay, and so what we can quantify is something called the radiant flux intensity. Sounds fancy, but it simply means the apparent brightness. The observed brightness, I think, would be an easier way to introduce it. The observed brightness, because someone standing on a patch of grass on their planet on A2 is going to notice much more of a dimmer image from the star than someone standing on a patch at A1. It can be two different planets, as an example. So we define the radiant flux intensity, which is the apparent brightness, as the luminosity L divided by the area over which that luminosity, which that power is spread. Okay, and A, that surface area, is simply 4 pi d squared, because the area is the area on the surface of a sphere, and the surface area of a sphere is 4 pi d squared. And so what we get is this thing, the radiant flux intensity, which we give the symbol F, is a power over an area. And so if I use square brackets just to identify the units of F, it will be watts per square meter, because we can see that the units of measurement for luminosity L will simply be a watt. It's a joule per second. If you want to write that down, joule per second. And so we now have this thing called the radiant flux intensity. We don't have to try and picture it too much, but what we have is the power over a unit area. And it is constant for a certain planet or for a certain location relative to a star, because, I mean, you should not be moving relative to that star if the star is anything that's significant to you, like the sun is to us. The sun and the earth aren't really moving toward or away from each other. And so we can get a fairly good idea of what the radiant flux intensity is, provided we know the luminosity. That's where things can get a bit tricky to figure out the luminosity. We can't simply just waltz over to the nearest star other than the sun and figure out its energy output. It's going to take a little bit more than that. Okay, so remember this equation. This is the radiant flux intensity. It's the luminosity divided by the area over which that energy is being spread. So it's an energy per unit time per unit area in that sense. And so if I wanted to define a standard candle, I guess to define it I would just use your usual textbook definition, which would be as follows. So a standard candle is a class of stellar object which has a known luminosity and whose distance can be determined. So it's a very specific definition. If I know the luminosity of something and I can figure out its distance, I'll call it a standard candle. Why? Because I can use it in the equation for radiant flux intensity, and I can actually find what's really important here is finding the distance d. Because if I find the distance d, I find the distance that the star is from the observer, which in this case would be us. So we know exactly how far the star, or not just the star's surroundings are from us, which is a very important measurement that we need to make in astronomy. And so a type of standard candle, there are many different standard candles. A supernova could be one. Basically, we look for very, very bright objects out in the universe. We look for the brightest objects that we can see, and we use them to make our measurements. We gather the light, we use Earth-based telescopes, space-based telescopes, etc. to gather as much light as we can to make an inference about what star we're looking at. And the best things to look at are the brightest things out there, because they give us more light to work with. And so there's something called a Cepheid variable. A Cepheid variable, the name might be a bit confusing, but it's simply a star, a very, 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 very bright star. Now, note that all stars are not necessarily yellow or orange. Our sun is a yellow-orange star, but our sun is actually a very small star. There are much larger stars in the universe that are bigger and brighter, but this is just an example. So a Cepheid variable is a very special type of star. It's one that goes from bright to dim and then to bright again periodically. There's an oscillation that happens with a Cepheid variable. And so at one moment it's bright, later the same star is dim, and then goes back to being bright again. And all of this happens in a time t. And what we notice, what is very special about Cepheid variables, is this time is a constant. It's a constant period. And that gives us quite helpful information. So what this means is that we can determine a relationship between the brightness of a Cepheid variable and the period of its oscillation between bright, dim, and bright again. If we think of the oscillation of the star as going from bright to dim back to bright, and we find that the luminosity is proportional to this period. And that's the graph that you see in your textbooks. You see a graph of luminosity versus period giving you a nice straight line. But wait a minute, this L is a very important thing, because we saw it in the equation for radiant flux intensity. F is L over 4 pi d squared. Wait a minute, if for a Cepheid variable F and L are known, we can find d. We can find the distance to that star. But actually we're finding much more than just the distance to that star. We're finding the distance, roughly, to the galaxy to which that Cepheid variable belongs. And so d is a very important measurement. So if we can somehow figure out what the luminosity of the star is given its relationship to its period, we know the radiant flux intensity because that's what we measure. That's the value that we measure on Earth. Well, we have L, we have F. 4 and pi are constants. We can simply find the distance d. And so now we actually can tell how far away the Cepheid variable is, how far away the galaxy is, and other objects that are surrounding that Cepheid variable. We don't expect a star to be a lone star in the universe. It should be part of a galaxy. And so a lot more information can be taken from this observation. So that's why Cepheid variables are important. And reading up extra pieces of information, maybe doing a little bit of background reading on Wikipedia or Khan Academy, will really help you understand maybe a little bit more on things like Cepheid variables. The extra reading will go a long way. As you can see, this topic is fairly conceptual, not very mathematical. Okay, but the understanding is very important, especially because we're dealing with large distances, large sizes, not your everyday objects. And some things even where Newton's laws break down and don't work anymore. So there is weirdness to it. What also is important to us, as well, at least as astronomers, is black body radiation and stellar radii. So stellar radii is a subtopic. Now basically all this means stellar is another name for star, and radius is telling us the size. So basically we can use some very simple methods to find out the size of stars. And so we have to define something called a black body radiation. Now what is this term black body radiation? Very simply put, all this means is that any black body in the universe, anything that is a black body, like a star, is classed as a black body. Most stars are classed as black bodies. Simply means that the radiation that they output, the energy that they output, comes with different intensities and these intensities happen at different wavelengths. Simply that the body emits radiation over a wide range of frequencies and hence a wide range of wavelengths, all of the colors. So the sun, for example, may seem yellow simply because the intensity of the yellow light is much higher. There's much more yellow photons being emitted from the sun than the other colors, but they are still photons from red all the way to violet, and even some ultraviolet and some infrared. But the majority that we see come in the yellow-orange color band, which is why we get the color that we see. So there's a nice diagram that you may see in your textbook called Stefan's law, or the Stefan-Boltzmann diagram distribution, which is a graph. I'm just going to sketch this graph. It's the graph of intensity against wavelength. So yes, again, this may be drawn as a logarithmic graph, or it doesn't really matter what the units are, but a very important relationship comes out. And so if I draw a blue spectrum, I get this shape occurring. I'll explain what this is in a moment. And then that's a blue star. Think of a blue star. And then a slightly more green star has a similar shape, but a slightly adjusted peak. The peak is a little different. It's shifted slightly to the right. And then a red star has a much lower peak, which is also even still shifted to the left. And so what I get is three different wavelengths, well, multitude of different wavelengths for different intensities, but since I'm only considering three colors, I get three different wavelengths, one for red, one for green, and one for blue. And now for blue, this usually corresponds to a temperature of 12,000 Kelvin. For green, this corresponds to a temperature of 6,000 Kelvin. And for red, this corresponds to a temperature of 3,000 Kelvin. So there's a lot of information in this graph. Basically, and this wavelength, we'll call it lambda max. Now, lambda max, as you can see, we have drawn the dotted lines, corresponds to the point at which the wavelength at which the intensity is a maximum. And so for a blue star, the wavelength for which the intensity is a maximum is obviously much less than for a green star. And the wavelength for a green star is less than that for a red star, which makes sense. Blue has a shorter wavelength than green, which has a shorter wavelength than red. But also what's important to note is that each of these colors have a different temperature. For red, it's 3,000 Kelvin. For green, it's 6,000 Kelvin. And for blue, it's 12,000 Kelvin. If you've ever seen someone maybe tempering a sword or tempering any steel, for example, and when the steel comes out of a furnace, it glows. It glows a very red or orange color when hot. It turns out that when objects are heated, they emit radiation, and depending on the amount of heat energy given to the object, the radiation is of varying wavelengths. So hot objects generally glow orange, red. But if I were to heat the steel any further, if I were to increase its temperature any further, it now starts to radiate through much shorter wavelengths, to much higher frequencies, much higher energies. And instead of looking orange, it'll turn blue, or even white. White hot is a much hotter hot than orange. And so this is basically what this distribution tells us. So red stars have their peaks, obviously their intensities, most of their wavelengths have on the red end of the spectrum, and so the intensity for red photons is much greater. And blue stars have the opposite. They have much more blue photons being emitted. What is important is we can tell by looking at the colors what temperature they will be. And so I think his name was Wilhelm Wien. From this, found a very simple relationship, which we call Wien's displacement law. I don't think of displacement as simply what you remember from kinematics, but what this means is this wavelength that corresponds to the maximum intensity is proportional or inversely proportional to the temperature. Sort of makes sense though, because as wavelength gets higher, frequency gets lower. As frequency gets lower, energy gets lower. And so wavelength and temperature, we'd expect energy and temperature to be related, directly related, which they are. And so wavelength and temperature are inversely related. And so if I wanted to turn this into equation, I would write this as lambda max is B over T. B is simply Wien's displacement constant, which is 2.898 times 10 to the minus 3. And be very careful with the units here. This is meter Kelvin. It's not millikelvin, it's meter dot Kelvin. And so this is very important because I can use this expression to find the temperature or to find the intensity, or rather the wavelength of the radiation that's being released. Generally, if I do a simple spectroscopic analysis of any light that's coming from a star, I can find lambda. If I find lambda, I can tell the temperature using this simple expression. So quite powerful actually. We can find the temperature of any star if I can see its color. With some of the equipment we have, even though stars are very, very, very far away, we can tell the light that is coming from those stars. And we can hence tell their temperatures. And so we can easily see that the light from the sun is more orange in color, and so we can make an inference of its temperature. Looking out further, we look at more blue and white stars and we can tell their temperatures as well. We know they will be much higher. And so we come to something known as the Stefan-Boltzmann Law, also hugely important. Not only does it have application in astronomy, but in other areas of science as well. So if I take any spherical object, it doesn't necessarily have to be a star. We're lucky that everything in the universe that is cosmologically relevant is circular, spherical in size, or in shape rather. And so what I have is a star or any celestial object with a temperature T, with a radius R. I'm just going to label this as spherical object. Doesn't necessarily need to be a star, like I said. So any spherical object that is radiating energy because of its high temperature has a luminosity L that is equal to 4 pi, the Greek letter sigma, R squared T, the absolute temperature raised to the power 4, where sigma is the Boltzmann or the Stefan-Boltzmann constant, and this is 5.67 times 10 to the minus 8 watts per square meter Kelvin to the power 4, which we can see if we were to just rearrange this equation. And so this equation gives us a relationship between luminosity and temperature. Okay. So luminosity was the thing we wanted to find at the very beginning. We said if we know luminosity, we can tell what the distance to that object is, whatever the celestial object may be, since radiant flux intensity is what we measure on Earth. So luminosity is the difficult one. But I can find the luminosity if I sort of have an idea of the size of the object or the temperature. Or actually vice versa. If I know the luminosity, I can find the size of the object, since Wien's displacement law will tell me what the temperature is. Aha! So this is why we call the subtopic stellar radii, because we can use the Stefan-Boltzmann Law to find the size of a star. And usually what we notice is that small stars, like the sun is a small medium star, are more red, orange, yellow in color. Bigger stars are generally blue and white in color. So they have higher temperatures. They also have larger sizes, but unfortunately that means they also live a much shorter time, as they get through their hydrogen much quicker. Okay, so we can use all of these expressions now to link things together. If I know luminosity and I know temperature, I can find the size of any celestial object. Luminosity can be found like we did before from using standard candles. Temperature can be found from Wien's displacement law. And hey, guess what? We can actually find the size of the object that we are receiving the light from, even though we can't physically observe or measure the size of that star. So these are all quite powerful methods that we're using. Again, I would suggest putting some time into doing the extra reading and seeing the applications of all of this. But for the purposes of the crash course, we'll just keep it simple. And so then we come to something called a redshift. And basically what we notice is all stars have hydrogen in them. And so because of the hydrogen gas surrounding the star, what we observe when we observe the light from any star is a range of frequencies minus the hydrogen spectrum. So generally, if I look at a near star, like the sun, for example, or any of our nearest neighbors, I get the hydrogen spectrum. I'm going to draw it in blue. So these are the absorption lines, the frequencies that I absorb. So everything in between would be nice and colorful, look like a rainbow, and these lines would be quite dark. Remember to go back to the topic of quantum physics to do a recap basically on what the absorption and emission spectra look like. But basically this is the violet end of the spectrum and this is the red end of the spectrum. And very specific lines are missing. And I know, and we know that this is the hydrogen spectrum. So the star is absorbing the hydrogen lines and emitting everything else, which means that there's hydrogen visible on the star. But that's not the weird part. That we've accounted for in the topic of quantum physics. But what we do notice is that for a distant star, we get almost identical lines occurring, but these lines are shifted. We still have violet and red, and we still have the separation of lines. I mean, this pattern at the top looks like the pattern at the bottom, but the pattern at the bottom is shifted slightly towards the red end, of the spectrum. Now, this is not just a once-off case. This happens for many different objects that we look at in the universe. In fact, most of the objects we look at in the universe, most stars, show us this. And all stars belong to a galaxy of some sort. So looking at the absorption spectrum of hydrogen for distant stars, we notice something very weird. All of them seem to have the hydrogen spectrum being absorbed, but it all seems to be shifted slightly to the right. The pattern is occurring. So what this means is that these stars are being redshifted. It means, like the Doppler effect, since they are moving away from us, their wavelengths are being stretched out. They're being shifted towards the red end of the spectrum. So this is very similar to the Doppler effect. You can think of it in that way if you want an analogy. But simply, if I think of the light wave that originally leaves a star, a very, very distant star, at the source, this is what the original light wave looks like. But what happens if the star is moving toward us, and we observe it, you can think of the same wave moving, so the source is moving with the wave, and so what happens is the frequency increases and the wave is sort of squashed together. And that means that the object is moving toward the observer, or toward you, just like it is in the Doppler effect. But if the opposite happens, if I notice that everything I look at has a much shorter frequency and much higher wavelength, and the Doppler effect tells us that the object is moving away from us. And if I look at everything in the universe, most things have this redshift to it, which tells us that things are moving away from us. So this is a hint that the universe is expanding. It's actually a very much more than a hint. It's conclusive evidence that the universe is expanding. Everything is moving away from everything else. And so if you look at your textbooks or find the derivation online, there's an equation that's very important, which says that the shift in wavelength, the change in wavelength, where delta lambda, if the original lambda wavelength is lambda and the new wavelength, original wavelength is lambda naught and the new wavelength is lambda, then delta lambda over lambda, where delta lambda is simply lambda minus lambda naught, is equal to the shift in frequency divided by the original frequency. This will be lambda naught, it will be f naught, and very importantly, it's equal to this expression v over c, where v is the speed of recession of the thing that is moving. So basically, let's take a star. I observe a very, very distant star, and it looks quite red. So I can tell, because I know so much about the universe, I can tell that the star shouldn't be as red as it is. Or any object in the universe that shouldn't be red looks red, and then I determine, well, that object must be moving away. And so if I'm on Earth, ignore the poor drawing, if I'm on Earth and I observe that this star, which is attached to a galaxy, which is all moving away from us, is moving away at some speed, if I figure out by looking at the absorption spectrum what the shift in wavelength is and what the shift in frequency is, then I can tell how far, let's assume I'm stationary. I don't have a special place in the universe, but I can assume that me being stationary is, I'm the frame of reference for this measurement. And so this star, this object, this galaxy, it's moving away from us at a speed v, and by using this equation we can find this speed in terms of the speed of light, as a fraction of the speed of light. And it turns out that things that are very far away have a very high value of v, and things that are very close together have a very low value of v. I mean, for the person sitting next to you, or your next door neighbor, you don't physically notice them moving away, do you? And that's because at closer distances, things are not the universe is not expanding as it is at larger distances. And so what we notice is that if we have a positive value for delta lambda, so obviously lambda minus lambda naught, the wavelength's getting bigger, this is positive. If we stick to the conventions that we've used here, then this implies a redshift. And if the change in wavelength is negative, then this implies a blue shift. There are objects in the universe that are moving toward us. Not all and not many, but if they are moving toward us, we notice a blue shift. We notice their wavelengths being stretched inward and becoming smaller when their frequencies become higher. Remember, frequency and wavelength are inversely related. And so this brings us to Hubble's law. Again, interesting to read about Hubble's law. I mean, this was discovered by Edwin Hubble 100 years ago, but with very, I guess I can say, rudimentary equipment if you compare it to what we have now. Edwin Hubble made a very important discovery. He found that, like I said, if I measure the speed of recession of some random Cepheid variable, of some random star, of some galaxy, we're going to stick with the idea of galaxies, because remember, a galaxy is simply a collection of stars and planets and other celestial objects. Some of them have a supermassive black hole at their center. If we measure the speed of recession and we compare it to the distance of the galaxy, and we'll measure this in megaparsecs. This is simply another unit of measure which we'll define later on. We get a fairly good straight line graph. You'll see Hubble's points fluctuate, but the points themselves all have a very linear trend to them. And so what Hubble said was there's a relationship between the speed of recession and the distance that the galaxy is from the observer. And obviously this is some constant times d, because I plotted v on the y-axis and d on the x-axis, and so I must have a constant gradient, which he called h0. And this law is known as Hubble's law. Now note that, yes, I said this is 100 years old, and we have since got better models to explain the universe. These are the most basic. These are the ones that will make sense if you're doing a first course on astronomy and cosmology, which I guess most of you are. And this thing h0 is called Hubble's constant. And Hubble's constant has a value of 2.4 times 10 to the minus 18, and I'm going to write this in a very special way, meters per second per meter. Now I know what you're thinking, this is simply per second. But let's think about what this tells us. What this means is that the recession of any distant object is 2.4 times 10 to the minus 18 meters per second for every meter that it is away from us. So the person sitting next to you, a meter from you, is receding from you at a speed of 2.4 times 10 to the minus 18 meters per second. This is a non-observable, this is a negligible amount, and this is why you can't observe things at a close distance actually moving away from you. But if the number of meters gets very large, then this value obviously gets much larger. V gets much bigger. And so the speed of recession is much greater. And so we can use this equation to do a very rough estimate of, well, how fast things are moving away from you. May not be exact, but it works fairly well. And like I said, even though we have better methods, it's still a very good method. And again, it's 100 years old. So let's define a megaparsec. A megaparsec is simply an astronomical distance, a distance. We're not going to talk about where it comes from, but basically it's 3.09 times 10 to the power 19 kilometers. Remember, in astronomy and cosmology, we have distances that are quite large. And so it doesn't make sense to be using meters and kilometers to measure these large distances. Now you're probably wondering why Hubble's law is really that important. Well, to answer that question, let's move backwards. I think if we move backwards, this makes a little bit more sense. Well, let's take a galaxy. Again, just going to draw it poorly, but there's a spiral galaxy. Maybe it's ours. And then there's another galaxy. we're going to move backwards. We're going to say that instead of these galaxies separating like we know they are, let's assume that they are moving toward each other. Let's go back in time. Let's move backward in time to the point at which they were together. If they're moving away from each other, at some point they were at a common point. In astronomy, we'd call that point the point of the Big Bang, where everything moved away from each other. Okay, and so we're going to basically go back in time to the start of it all. So we're going to try and find a way to find how long these two things have been moving away from each other. And they have a relative speed of v. Now, we know that the time that they've been moving apart is the distance over their speed. Okay, that's fine. That's the distance divided by, now if we use Hubble's law, that's h naught d, or in this case h naught x, we get something very impressive. The x's cancel, we get t to be 1 over h naught. That's the time over which these galaxies have been spreading apart, or the time over which they would need to come back together if we reversed everything, is, let's put Hubble's constant into this equation. 1 over 2.4 times 10 to the minus 18 seconds, or rather per second, and we get t to be 4.2 times 10 to the power 17 seconds. What does that mean? That means that these galaxies, in spreading apart, going at a speed v, have, again, roughly, very roughly, been traveling for 13 billion years. That means, as we understand it, the Big Bang happened 13 billion years ago, which means this value, 1 over h naught, t is 1 over h naught, is a very important equation. It tells us the age of the universe. So 1 over Hubble's constant gives us the age of the universe. That's why, although very rough, and current calculations tell us that the universe is more like 13.8 billion years old, but even still, 100 years ago, to get measurements as accurate as this is still quite impressive. And that's why we deal with Hubble's law. It's not simply the fact that we use a very simple linear equation to add more content to a topic just to make your life any more difficult. It's literally because it has such a profound impact, such a profound meaning in the topic of astronomy and cosmology. So 1 over Hubble's constant gives us the age of the universe. Like I said, there's a lot of gaps to be filled, and a lot of information that you can glean from other sources, which will just help your understanding. But as you can see, the mathematics is not difficult. If you study your quantum physics well, learn about line and emission spectra and absorption spectra, the topic is not that challenging. It is novel, but can be overcome with a little bit of reading and understanding. So until next time, I am Mr. K, and this is Everything is Relative. Good luck with studying.